Okay, let's just get right into it. When you first stare at the readout from a mass spectrometer, honestly, it can be incredibly intimidating. You are presented with this jagged, chaotic landscape of lines and numbers. But I want you to completely reframe how you look at these graphs. We're not going to think of this as a bunch of abstract data points. Instead, think of it as a thrilling forensic investigation. A molecule has literally been blown apart in a vacuum chamber, and we are the chemical detectives stepping onto the crime scene, piecing together the true structure of our victim based purely on the fragments left behind. So that brings us to the ultimate question we're tackling today. How exactly do you turn that jagged graph into a perfect 3D molecular structure? The raw output from a mass spec is basically a chemical fingerprint. Every single peak you see is a clue, a crucial piece of structural evidence just waiting to be decoded. But to do that, you absolutely need a strategy. You can't just guess your way through it. You need a rock-solid, reproducible system for analyzing experimental data alongside other spectroscopic methods to deduce that final, elegant chemical structure. Here is our roadmap for today. We'll start with the concept of the spectral detective. Then we'll find our molecular ion, decode isotope clusters, cover the actual rules of fragmentation, build out a strategic playbook, and finally, we'll solve an unknown compound together. Part 1. The Spectral Detective. We live in an incredible age of technology, right? If you have a digitized mass spectrum, a basic computer can compare it to a library of tens of thousands of spectra in a matter of seconds. It gives you this neat little hit list of suspects based purely on probability matching. It might tell you, hey, there's a 94% chance your unknown liquid is 1-chloro-2-methylbenzene. But there is a massive difference between relying on automated computer searches and actually having the skills to interrogate the data yourself. What if your novel compound just isn't in the database yet? Or what if it's a wildly complex natural product? A true chemist can't just blindly trust a hit list. We have to manually verify the evidence. You really need to know the why behind the data. Moving on to part 2, finding the molecular ion. Our investigation has to begin with finding the intact body of our molecule. We call this finding the molecular ion. When we look at the electron ionization mass spectrum of something like butane, we are basically bombarding the molecule with high-energy electrons. Initially, the molecule loses just one electron to form a radical cation, and that is our molecular ion. It sets our baseline true mass, assuming we ignore heavy isotopes for a second. In butane, you'll spot this at a mass-to-charge ratio of 58. Now, if you compare that relatively small peak at 58 to the absolute massive spike at 43, that tallest peak is what we call the base peak. It represents the most abundant fragment that formed when our butane molecular ion broke apart. But here is a massive catch. You have to be super careful to ensure the peak you're looking at is actually the molecular ion and not just a heavy fragment. Beware of the invisible molecular ions. If a molecular ion is highly unstable, it might have a lifespan of less than 10 to the minus 5 seconds. It will literally shatter into fragments before it can even make it to the mass analyzer. If that happens, well, our strategy has to adapt. We might have to switch to a much milder technique, like chemical ionization, to gently protonate the molecule and find its mass, or we have to play the ultimate puzzle game and deduce the original weight by piecing all the fragments back together. Part 3. Decoding isotope clusters. Once we actually know the mass of our suspect, we can start hunting for specific atomic evidence. Molecules in nature just aren't isotopically pure. Atoms have heavier isotopes that occur in highly predictable natural abundances. And these heavier isotopes leave very distinct signatures. Halogens, for instance, act like glowing structural beacons. Take ethyl bromide. Bromine exists in nature as roughly a 50-50 mix of two isotopes. Because of that, any molecule with a single bromine atom is going to show a really obvious 1-to-1 ratio for the M and M+2 peaks. Now contrast that with dichloromethane. Chlorine's isotopes exist in a 3-to-1 ratio, and since that molecule has two chlorines, it creates this beautiful, messy cluster for the M, M+2, and M+4 peaks. Without even looking at the rest of the fragments, the isotopes alone immediately tell you exactly what halogens are crashing the party. All right, part 4, the rules of fragmentation. Finding the molecular ion and spotting those halogens is really just step 1. To truly solve the 3D structure, we have to understand exactly how the molecule breaks apart. Under electron bombardment, chemical bonds do not just break randomly. They fracture at various specific weak points following strict chemical rules. The primary motive behind these fractures is governed by Stephenson's rule. This essentially states that the most probable fragmentation is the one that leaves the positive charge on the fragment with the lowest ionization energy. But simply, Molecules break apart to form the most stable ions possible. This is the exact same logic as Markovnikov's rule from your standard organic chemistry class, where you form the most stable carbocation. The same things that stabilize carbocations in a beaker stabilize fragment ions in a gas phase vacuum. Then we've got the even electron rule, which is an absolutely vital tracking tool for our investigation. When your odd electron molecular ion fragments, it usually yields a radical and an even electron cation fragment. But that even electron ion, it can only further fragment to create another even electron ion and a neutral molecule. Knowing this rule is a total game changer. It helps you accurately predict and track valid pathways so you don't waste your time drawing chemically improbable or just downright impossible structures. And of course, I have to mention the famous McLafferty rearrangement. Most cleavages just snap a single bond, but this one is a complex signature rearrangement. It involves a 6-membered ring transition state that ultimately produces an alkene and a completely new radical cation. If you see the specific mass losses associated with this rearrangement, it's a massive, definitive clue pointing straight to specific functional groups, like a ketone with an alkyl chain attached. It really cuts right through the noise of the data. Part 5, the strategic playbook. We have our rules, we know what we're looking for, so now we put them into a reproducible sequence. This is our strategic playbook for interrogating literally any mass spectrum, because true problem solving requires a real strategy. First, take a thorough inventory. What is the sample's chemical history? Do we have infrared or NMR data we can cross-reference? Context is absolutely everything. Second, clearly identify that molecular ion and check its isotope cluster. Third, analyze the high mass peaks to determine if the mass losses are odd or even. Like if there's no nitrogen present, an odd mass loss usually means a simple cleavage, while an even loss hints at a complex rearrangement. And finally, step 4, look for recognizable fragments and piece them all back together. Continually compare your proposed structure back to the raw data to see if it holds up. Part 6, solving an unknown compound. Okay, it is time to actually put our playbook into action. Let's take on the role of chief investigator and solve a real unknown chemical case together. Here's our evidence file. First up, the inventory. We have an IR spectroscopy clue, a peak at 1688 inverse centimeters. That strongly suggests a carbonyl group conjugated with a benzene ring. Next, we check our mass spec data and pinpoint the molecular ion at M/Z134. If we apply the rule of 13, which is a brilliant little mathematical trick to deduce formulas from molecular weight, we get a highly probable formula of C9H10O. This aligns perfectly with our IR clue of a conjugated ring system. And finally, we look at the fragmentation clues. We're seeing major peaks at 105, 77, and 51. Now we piece the whole puzzle together. Our molecular ion is 134. Our first major fragment is sitting at 105. So that's a mass loss of 29, which corresponds flawlessly to the loss of an ethyl radical. But even more importantly, that remaining fragment at MZ105, that is the classic mass of a phenylethylenedium ion, a benzene ring directly attached to a carbonyl carbon. This matches our initial IR data beyond a shadow of a doubt. Our suspect is fully reconstructed and identified. It's propophenone. We just use strategic deduction to prove the structure, entirely from the clues left behind. So what does this all mean for us? As we have seen today, mass spectrometry is way more than just reading a graph. It is a genuine art of deduction. It requires integrating physical rules, spectroscopic context, and real chemical intuition. So if a computer algorithm can just spit out a probability hit list in a few milliseconds, what are the actual dangers of relying entirely on software without cultivating this human intuition? Well, when you're dealing with entirely novel compounds, strange biological unknowns, or unprecedented chemical architectures, the computer's library is completely blind. At the end of the day, only the chemical detective, armed with a strategic playbook, can uncover the true molecular truth.